This is 2.10. So, this question is a little bit tricky. The earlier one is actually a little bit more tricky, but this one, it's kind of intuitive. I like it a lot. So it says a ball is dropped from rest at height h. Another ball is simultaneously thrown downward with speed v, right, from height 2h. Oh, oops. Yeah, this would make sense actually. What should v be so that the two balls hit the ground at the same time? So this one's a little bit tricky because unlike the other problem, if you equate these two, right, the collision, the only reason you would equate them, right, is once they collide with each other. But the thing is, when you collide them, you get multiple variants of v, and that's because you can collide at maybe this point, this point, this point, any point that's after h, right? So it's a little bit harder, but there's a way to do this, right? So let's just start out with the obvious. Make these the equations. That's the first thing you always want to do. And remember, this is your equation for actually x and y variables, but this is y. So yo is basically 2h, right? The vot we don't know, so that's just going to be minus actually vot, right? Because velocity has direction and we're just going down. We're just going to say this is negative distance and speed. Yeah. And it's going to be half gt squared, negative half gt squared, again because the acceleration is negative. So that's our y for that. For here, we have the same thing. Unlike the other one, we have actually just h. The VOT is non-existent, it's dead, and the same thing happens here, negative half gt squared. So let's equalize these two. 2h minus VOT minus half gt squared. If you equalize that to h minus half gt squared, you get something quite strange actually. Let's get this. Negative VOT is equal to h minus 2h. Negative VOT is equal to negative h. We plus these because much nicer. T is now equal to h over VO. It's a very interesting problem because at this point in time, that just tells you that the time isn't even defined yet. We can have multiple points in time because there are multiple points in collisions when we equalize these two equations. But later on, you realize something else. If you want this to work, let's just plug in the t, right? Because automatically, originally, right, I thought, oh, it's pointless because you're just going to have 0. But that's not true. There are multiple points in collision, not just this point in collision, there's also these ones. And so when we plug in t, we can just solve for v, and we'll be done with the entire problem. So because this is VO, we have to go with this equation, because it's the only one with VO. And that'll really help us out. Or I guess you could do both, but I'm just going to try this one. 2h minus VO, h over VO. Yeah, it just cancels out, it's really nice. Minus half g h over VO squared. We get 2h minus h, right? Minus half g h squared over VO squared is equal to h minus g h squared over 2VO squared. Alright, and now all we gotta do is make this equal to 0, right? Because we want the y value, the final y value, to be 0. Because that's the point of collision that we want. And so, it's really easy from here on out. Negative h is equal to negative gh squared over 2VO squared. We basically just make these positive. We solve for v. 2VO squared h is equal to gh squared. Cross out the h. We actually still have an h here. 2VO squared is equal to gh. We divide and square root. So this is our final answer.